Let us see an introduction to the simplified instructional computer. So it's a hypothetical computer. It's used to explain the operation of the real computer. So it's a simulation only. We are not going to have exact one. In this, we are having two versions. One is SIC standard model and the other is SICXC. We are going to consider the SIC standard model. So the architecture of the SIC hypothetical computer is so similar to the real one. We have the memory, I/O devices, and CPU. And CPU is connected with the registers, the fastest memory. And for registers, it considers five registers, and the rest are left over for future adding. And the registers which are currently considered are A, accumulator, the next register for indexing, then L for linkage, to move between the subroutine calls, and then program counter and status word, okay, SW. And IO devices to represent the input device, output device. There is, and each device is represented by a value, okay, which is of 8 bits. And then memory we are having, which is starting from 4 zeros to 7 triple F memory spaces are there, which means 15 bits can be used for representing the memory address. So the total memory space available in this hypothetical computer is 2 power 15 bytes. Okay. And here byte addressing is used. So it starts from byte address 0, okay, and 8 bits as usual. 8 bits is making 1 byte. And for word, 3 bytes used. Okay. And 3 consecutive bytes are used for representing one word, which is 24 bits. And if I'm having a word to be represented, then it is represented by its lower numbered byte. Okay, so if I'm having a word, the lower number byte, suppose if the first 3 bytes are used for a word to be represented, then the 0 will be used to address the word. Okay. And the registers, as it is already said, accumulator A is the register representing the accumulator used for arithmetic operations. Then the register X is used as indexed register to represent whether it is direct addressing or indexed addressing. Then L is a linkage register to store the return addresses when I'm having a subroutine call. Once the subroutine is getting over, when it gives the R sub return sub instruction back to come back. So it will store the return address in this register. When there is a J sub call, jump to subroutine call, the next line's address will be stored in this L register, linkage register. And then PC, program counter, it gives the address of the next instructions which is to be executed. And then status word, it contains the condition code of every comparisons. Okay, if I'm having some comparison with some value, and if I have to jump to some other places in the program based on the result of the comparison less than, greater than, or equal, so that result will be stored in this status word, okay, including the condition code. And then the data formats are, integers are represented by 24 bits. Make a note of this. Integers are represented by 24 bits. Then negative numbers are represented in 2's complement. And characters are represented by 8-bit ASCII values. So character by character only we are considering. If it is a string, we are considering it as sequence of characters only, and they are represented by its 8 bits ASCII value. And there is no floating point representation in SIC. And the instruction format is first, so each instruction will be of 3 bytes, and first byte 8 bits, that is used for the opcode. For example, it can be LDA, STA, okay, or comparison, so these are the opcode we'll be having. Its mnemonic will be stored in the first 8 bits. Then in the remaining 16 bits, 1 bit is used for indexing to represent whether it is direct addressing or indexed addressing. And the next 15 bits are for the memory reference. So an example for direct addressing and indirect addressing. If I'm having an instruction LDA 10, 10 is a symbol, a label is referred here. Uh, so in 10, we are having the word. So I'm having in 10, we are having a word 10 is stored. So word is actually used for representing the integers. So 10 is given here. So now since there is no index register value, directly the 10 will be taking the address 11050 and this value will be referred over there. So 10 will be loaded in the accumulator. So the target address is 1050 itself. But if I'm having an instruction LDX to load the index register X with the value at 0, what is at 0? In 0, the value 0 is stored. So the X will be stored with the value 0. Now load the character str1. At str1, what we are finding is TEST, a string of characters is given. Okay, so they are represented by bytes. So TEST, individual characters I'm having. So in STR of 1053, starting from 1053, I'm having the sequence of characters TEST, which means at place 1053 I'll be having T, and at 1054 we'll be having SE, and then this will be available in the position 55, and this is at position 56. So now with the address 1053, this x value will be added. What is the value of x here? It is having the value 0. So that 0 is added to 1053 and it is referred. So here also the target address is 1053 since x is loaded with the value 0. And let us consider another example. Now LDX is stored with the value 2. So X is loaded with the value 2. At 2, what value is found? The integer value 2 is found. Next, we are having load character. Accumulator should be loaded with the character at str. So at str, X, since it is an indexed addressing, the X value should be added with str. So what is str? 1053. So with 1053, this index value should be added. So now we are getting the target address as 1055. So at 1053, we'll be having the letter A. Starting from 1053, the sequence of these characters are stored. So up to 1057, this word is stored. So now I'm having the target address as 1055. So at 1055, we are having the letter C. So the accumulator now will be stored with the value C. So likewise, the index register is used for representing the indexed and direct addressing. So memory address this is referred. So A will be stored with C. And the instruction sets are the load and store instruction. So we are having LDA, STA, LDCH, STCH. Okay, loading with the integer value will be calling this LDA. If it is a character, then we'll be having LDCH. Similarly, loading and storing the index register, and then the arithmetic instructions, examples add, sub, etc. Then comparison instruction. Uh, we'll be having the comp data, comparing the data with a particular value, and then we are having conditional jump. So conditional jump based on the comparison which is done in the previous step, we'll be checking whether it is less or equal or greater. So this comparison answer will be available in the status word. Okay, and using that value, it will be checking whether it is less, greater, or equal. Based on that, the jump instructions will be executing. Then subroutine linkages, we are having jump to the subroutine and return from the subroutine. An input output performed by transferring one byte at a time. Okay, and each device has an 8-bit unique code. Okay, whatever input devices we are referring, each will be having 8-bit unique code. And for testing that input output devices and to read and write in the devices, we are having test device instruction, TD. Okay, to test whether the input device is ready for the operation to be done. Okay, if it is an input device, whether it is ready to read from. If it is the output device, whether it is ready to write into. So that test device, and that result will be stored in status word. The condition code will be stored in the status word register. And if that CC is less than, if I'm having jump less than, if that is true, means the device is ready. Okay, otherwise if it is equal to 0 means, if it is equal means, then it is not ready. Okay, and to read from the device, RD is used, and to write into the device, WD is used. Okay, so it will take the content, read the data into the A register, and write the data into the A register. Then the basic assembler function. So we'll be applying, we'll be using this SIC machine to understand the concepts of the system softwares like assembler, macroprocessor, linker, and loader.